All right. Okay, so I don't know if you guys maybe dialed in or tuned into the webcast this morning. There were like a bunch more views on there than normal, which I was stoked about. Did you guys tune in?
Yeah. That's about color code.
You got color coded and everything?
Well, I found like my highlighters like last minute. It's on color code when I get home. But yeah, I did watch it.
Well, good. Got this hair in my mouth that's just driving me up the wall. That's excellent. If I had realized that you guys were getting tuned in, I would have told all the morning kids to tune in this afternoon because we could have gone on. But I guess what I'll do is quickly recap the morning because, and if you're tuning in too, good. Because honestly, this is a really important one. This is the context for everything else. So like even hearing it twice is a good thing. And colored pencils are there if you need to color code. West Coast tectonics, aka North America crosses Farallon plate. So let's see. I guess you guys are getting set up. I will make 3 crappy drawings of the West Coast. There's a super crappy drawing of the West Coast. Right, so we were 40, 20, and 0 million years ago. And so this is the evolution of West Coast geology, and it is all like I said, this is the scene against which we are framing basically all the rest of our class. Got that one. We got this one. And we got this one. And so we're going to color code and label all of these things. I'll do it quickly since you guys tuned in. North American plate, the Pacific plate, Pacific to the northwest, North America to the southwest, and this little guy in here, of course, Juan de Fuca plate. Opening up like that. So we had divergent plate boundary here, here, a little bit there, and also a little bit of the East Pacific rise down here. Also divergent. Get that in red. And I used green to put our San Andreas fault on there. And we have this other San Andreas style fault called the Denali fault up here on the west coast of Canada. Transform plate boundary. Then using our blue, we put in a bunch of blue X's for Cascade volcanoes from British Columbia down to Northern California. And a blue line right here indicating subduction, a convergent plate boundary. And I didn't point this out this morning. I should point this out. I thought to point it out this morning. I almost pointed it out this morning. We started with a way simpler, like at the beginning of this class, we had way simpler rules. We said North America is moving west. And we said that the Juan de Fuca plate, that's moving east. It's subducting beneath North America. Well, now we've got this diagram where Juan de Fuca is going to the southeast and North America is going to the southwest. And the thing that I want to point out about this is this is some good vector, and it works for the San Andreas fault too. San Andreas fault, you've got Pacific plate going to the northwest, and you have North American plate going to the southwest. And if we look at those and separate them into west and north components and west and south components, basically the Pacific plate and the North American plate are moving west at the same rate. So that goes away and that goes away. They're moving at the same rate to the west. So on the San Andreas fault, the only thing we really have is this north-south, with the Pacific plate going north and the North American plate going south. Same thing is true up here, the Juan de Fuca plate. Oh, that one's almost bad. Let's try this one. Juan de Fuca plate and the North American plate. We've got Juan de Fuca going to the southeast and North America going to the southwest. We can separate those into a south component and an east component and a south component and a west component. And so with Pacific and North America down here on the San Andreas fault, it's the west motion that cancels out because they're both moving west at the same rate. With Juan de Fuca and North America, it's the south motion that cancels out. They're both moving south at the same rate, so the two plates, the only motion that really matters with that subduction ends up being this east-west stuff. So there's a little bit of math. I don't know if any math classes in this entire school talk about vectors, but there's a little vector lesson for you. We also have some cascade-style volcanoes up here in Alaska and subduction. We also have some cascade-style volcanoes down here in Mexico and subduction. Anything I should have labeled that I did? Yeah. East Pacific Rise. And we've given this guy a name here, but that is the Juan de Fuca Ridge, where I suddenly start writing in lowercase for some reason. Juan de Fuca Ridge. Okay, so that was step one. This morning, we looked at the present day picture that we're comfortable with, that we know about. And then we jumped to 40 million years ago because that one goes really fast. We've got a divergent plate boundary, divergent plate boundary, divergent plate boundary, all in red. The simplest of pictures of the three. North America, still moving to the southwest. Pacific plate's out here. And the Farallon plate is right here. And we have a big, long, continuous chain of blue X's, of blue cascade-style volcanoes, all the way down from Alaska to Mexico. We still have subduction here, so we have subduction and cascade-style volcanoes here, as well as all the way down the coast. It is continuous from north to south, just like South America is today with the Andes. A couple little transform boundaries out here in the ocean, but those hardly even count for anything. If we really wanted to, we could come along and add some green transform for these little tidbits there too. Okay, and so the 20 million year picture, we kind of know it's just putting the two together. We've got Pacific, we got Farallon, we got Juan de Fuca, we got North America. North America is going southwest, Pacific's going to the northwest. Juan de Fuca is going that way, going that way. We've already started forming the Denali Fault. And right here, we just have this little baby, wee little infant San Andreas Fault here. Just barely starting to form. Of course, we've got our Cascade volcanoes here. And anywhere that we have subduction, which is most of California and all of Mexico, still, we should have a chain of Cascade volcanoes, Cascade-style volcanoes. Still divergent, divergent, divergent. And Alaska has been erupting for many, many millions of years. So that's pretty much what we did. That was pretty much the morning. With the color coding, we've had a chance to enrich your color coding experience. And hopefully we're feeling comfortable with this change in North American geology over the last 40 million years, because there's a couple of things, there's a couple of lectures that deal with Washington State that go earlier than 40. But a lot of what we're looking at from here on out till the end of the year is the last 40 minutes. And then this morning I used the questionable analogy of a runner crossing the finish line on a race. And the North American plate was the runner, and the finish line, that ticker tape pulled out across the racetrack. North America is running the race 40 million years ago. 20 million years ago, North America just barely gets across the finish line, and North America is still working on crossing the finish line today. The thing I didn't point out, morning group, I hope you're still with us, because putting this in context, I forgot to put one really important piece of information in there in my terrible race analogy, and that is this. If the finish line of the race is crossing the East Pacific Rise, and North America has been racing toward the East Pacific Rise, the obvious question that I should have asked this morning is this: when did the gun go off? When did the race begin? How long has North America been racing toward the East Pacific Rise? And the answer that you would be looking for is that the gun went off on this race 200 million years ago. That's when Pangea broke up. Pangea split up 200 million years ago, and that's when North America begins racing around the globe toward the Pacific, or toward the East Pacific Rise. And hopefully the thing that we can now see is that the Juan de Fuca plate and the Farallon plate are one and the same. They are the same piece of ocean crust that is slowly going away. It's slowly being taken over by North America. And I don't know if you guys caught this morning, but a crucial date. Juan de Fuca plate, it's doomed. It is not long for this world, geologic time speaking. We got about 10 million more years. 10 million more years of Juan de Fuca plate. 10 million more years of Cascade volcanoes, and those puppies are going to dry up just like the ones in California did. And eventually, 10 million years from now, this whole thing will be gone, and it'll be a solid green line from Alaska down to Mexico. So that's the backdrop. The scene is set. Those triple junctions are on there, the TJs. We don't really need to talk about those too much, but they're interesting to geologists. 37 has a nice cross-section sequence showing this kind of in cross-section, but it's 45 and 30 instead of 40. I don't know why I should have just made it the same, but whatever, maybe next year. So we've got 20 minutes, and I am going to launch into our next topic. And I guess I will blast through this in the morning for morning people who didn't tune in. Maybe I won't. Maybe I'll just tell them to watch this video. Our next sequence here, our next couple lectures, are much, much closer to home. Our next couple lectures are much closer to home, and we're officially beginning this one right now. And Columbia River salts field data. Columbia River, hey, that's in our backyard. Basalt, hey, that's the kind of rock that's all over the place. The Columbia River basalts here in eastern Washington are quite remarkable. I don't want to use the word unique because there are other places in the world that have similar rock formations, but they're very rare. And ours are the youngest of all of these types of rock formations. So there's a special term for this kind of rock formation, and they are called flood basalts. Flood basalts. Flood, like Noah's Ark and stuff? Nah, man, not like water flood, but like what water does in a flood. In a flood, water fills in all of the low ground everywhere. And there's a lot of it, and it covers everything. These are flood basalts because basalt lava came in, filled in all the low ground, and covered everything. So flood, not like water, but like a water flood behaves. It's a flood of lava, red hot, orange hot lava. Now, we've done a lot of learning the rules in this class, learning the patterns, you know, the igneous rocks at the margin and the craton and the platform and the granite, melted continental crust and melted oceanic crust and all of this stuff. We learned the rules and how the world generally behaves. The point of learning the rules is that when we find something that breaks the rules, we're like, oh shit, that's interesting. And this is definitely a thing that breaks the rules. Things we know about basalt. Basalt, that's the rock we're talking about. So things we know about basalt. Well, let's see. Little concept map here. We could put together all sorts of stuff. 45% silica. Ocean crust. Mafic. Dark rock. Hawaii. Gosh, what else? Mid-Atlantic Ridge, East Pacific Rise. Juan de Fuca Ridge. All of these places make basalt. Divergent plate boundary. We think of basalt as coming from divergent plate boundary. Okay, all right, cool. We know the rules. We know where we find basalt. We go to the ocean floor, except we're 600 feet above sea level, and this ain't the ocean, this is the desert. And there's no divergent plate boundary around here. But we've got a Hawaiian island worth of basalt sitting out here in eastern Washington. So this is a major mystery as compared to the rules that we know. How much basalt? There's a lot of effing basalt. There's Columbia River basalts in Spokane, in Ellensburg, in Moses Lake, down to the Tri-Cities, down to Bend, Oregon, all the way down the Columbia River Gorge out to the Pacific Ocean. Here in Mattawa, there is Columbia River basalt covering a major portion of the Pacific Northwest. That's one of the better ones. Columbia River basalt, it's got a footprint something like that, and even further south. Something like that. A big cow pie of this black lava rock that's supposed to be on the ocean floor. What is it doing here? Why is it here? How did it get here? And what does it mean? They're flood basalts because there's so much lava. There is just so much. And it didn't all happen at once. These Columbia River basalts henceforth abbreviated as the CRBs, formed in hundreds of individual eruption events. Hundreds of eruption events. We know because we can get absolute dates on lava rocks. We can get absolute dates. And so there's chemical differences between these different flows, and there's time differences between these different flows. Some flows traveled more than 300 miles. Freaking miles. Rivers of lava traveling 300 plus miles. Holy smokes. Average of 100 feet thick. Each flow, each of these eruption events creates a flow of lava that is an average of 100 feet thick. Big layer cake. It's like a wedding cake made of basalt with layer after layer after layer after layer after layer. It's like the layers of a cake, all nice and flat. Well, shit, man. If we got hundreds of eruption events and some flows that travel over 300 plus miles, we have hundreds of these things and they're all 100 feet thick. How thick is the whole deal? Like how much basalt are we talking here? So the Tri-Cities, where I was this last weekend, Tri-Cities is built on 3 miles of basalt. 3 miles. 15,600, nearly 16,000 feet of basalt. Straight down. We've got data that proves this. In the 1980s, the Shell Oil Company did some exploratory drilling around the Tri-Cities. They thought that maybe if they got down deep enough that they had reason to believe that there's some good oil and natural gas and stuff underneath all that basalt. And so the Shell Oil Company set up and they drilled these well holes down by Tri-Cities. And they had to go through 3 miles of basalt lava rock before they got down there. And there is oil and gas underneath the Tri-Cities. But it is so deep and that lava rock is so hard that it's not economically viable. It's not worth the time and money that it would take the oil companies to go recover it. So there it sits. Ages. The oldest Columbia River basalts. The oldest Columbia River basalts are 17 million years old. The youngest are 6 million years old. So what? Does that mean that this was happening constantly for 11 million years? It doesn't. Something like 97% of the eruptions was from 17 to, what did I say, 15.6. So almost all of it happens in the course of about 1.5 million years. And then it continues to spin for another 10 million years. So with hundreds of eruption events and hundreds of separate flows, which each makes a layer, as you can imagine, there's a lot of different names. You know, in the world of science, it's something people like to do. Like, if you can name something that nobody else has named, that's a big feather in your cap as a scientist. And so there's plenty of individual flows that have individual names. Sometimes a geologist will name a new flow down here, and another geologist will name a new flow up here, and they'll turn out later that they're actually the same flow. So then the same flow has 2 names, and that's just the way that goes. But where did it come from is kind of an obvious question. And maybe it's a good place to stop. As a matter of fact, it's a great place to stop. Columbia River basalts came. There's no mountain. I'm sorry, that's another thing I could have put up on my list of what we know about basalt. Shield volcanoes. I could have put a shield volcano up there, but there's no mountain. There's no volcano. There never was a mountain or a volcano. Well, it's a volcano. But the volcano wasn't a mountain. It was just cracks in the ground. So a crack in the ground would open up, and all this lava would just come gushing out. It would be a fountain of lava, and it would run all over the place, and then it would cool off, and then another crack in the ground would open up, and repeat, repeat, repeat. We have cracks in the ground in southwest Washington. Should have put them at a different angle, but cracks in the ground in southwest Washington. We have cracks in the ground in eastern Oregon, all the way down through eastern Oregon, and even in the very northern part of Nevada. Geologists have located these cracks in the ground. You can still go find them. They're still full of basalt. And we've got ages for these things. The earliest cracks in the ground, the earliest of these eruption events happen here. So this is like the 17 stuff down here, and the eruption site migrates north. These cracks in the ground get younger as you go north. So our ages, 17 to 6, well, 17, 6. And basically, the further north you go, the younger the cracks in the ground get. But it's like 17 to 16, and then all of this last stuff, the last 10 million years, is all of this southwestern Washington. And maybe if you thumb through your notes between today and tomorrow, 17 million years there in northern Nevada might start to sound a little bit familiar. So I will leave you with that, as we have 1 minute left. But this is some good foundational background information for our Columbia River basalts. So, that's that. Let's not forget, Tuesdays are new lab days. Last week it was a Wednesday, and I would like to get back to Tuesday, so I would like to get our new lab going tomorrow, which means I would like last week's lab to be done tomorrow. If that's too soon, I think maybe we'll do like tomorrow at the end of the day or something, so give you guys time to do that. But yeah, new lab tomorrow as well. Have a great afternoon.
See you tomorrow.